Hi there, my name is Lina Eklund and I'm a lecturer at the Department of Physical Geography and Ecosystem Science at Lund University, and I teach GIS and remote sensing there. And today I will have a lecture on studying drought using Earth observation approaches. So in this lecture we will talk about what drought is and also a little bit about what it's not. We will talk about drought and climate change, how it's linked, and then we will go into how we can measure drought. And then I will provide a short summary. So this is a quite short lecture aimed at giving you an introduction to the topic of drought assessment using remote sensing and other data. So first of all, drought is a condition of insufficient water availability or moisture. This means that drought refers to a period when there isn't enough water available. It's relative to what's normal. So it's about if you have water as normally you have or not. You can have a drought in a really wet area like a rainforest, but you can also have drought in arid areas close to deserts. There are several different definitions of drought. The most common one is probably meteorological drought, which refers to a reduction in rainfall, but also sometimes it includes an increase in temperature, which leads to increased evapotranspiration. So that's meteorological drought. It's the most commonly used definition, but it doesn't capture everything. So because of that, we have also other definitions that are linked to meteorological drought. For example, hydrological drought is when you have less water in rivers, in reservoirs, lakes, water bodies, or in groundwater reservoirs. So that's hydrological drought, and this often happens when a meteorological drought causes a reduction in, for example, groundwater levels or river flows. Agricultural drought is a condition where you have insufficient soil moisture and insufficient moisture in the soil to support crop growth. So this is where it starts to affect or get more clear how it affects people and their livelihoods. So agriculture is then when agricultural drought is when you don't have enough water to support the crops you're growing, for example. And then finally, I think it's important to mention socioeconomic drought, because this is a used definition of drought, but it's not as used as the other definitions. And I will come back to these definitions and how we can measure them. But I also want to highlight that drought has a temporal aspect, because if you have a drought for one day, it's not really a problem. It may be per definition a drought, but it's not necessarily a problem compared to having a drought over a month or over several months. So we have to consider the temporal aspect. For how long time do we have a drought? And then I also want to emphasize that drought is relative. It's relative to what's normal. So that means you have to look at what is the normal situation here. Is it normally very wet during a specific month, and then during a certain year it's not raining as much, or it's much warmer than usual? Then you have a drought. But you don't necessarily have a drought in areas that are always quite dry. So it's always about what's normal and relative to that. Okay? I also wanted to highlight a bit about what drought is not, because drought is often conflated with other water-related issues. And one example is water scarcity, which is actually a lack of sufficient available water resources to meet the needs for water within a region. So in the definitions I posed before, it was not so much about the needs, but about what's normal, what's the normal water availability. When it comes to water scarcity, it's directly focusing on what the human needs are within a region. So this is often also a more long-term issue. You have people and water demands not being higher than the availability of water, because there are many people living in an area, or the lifestyles have high water demands, for example. That's where you have water scarcity. It's not necessarily connected to drought, but it can be. Drought can, of course, worsen the situation. Then we have desertification, which is a type of land degradation. So here, quite dry areas of land become more and more arid, losing bodies of water. For example, lakes are shrinking, vegetation and wildlife is affected. And this is also not necessarily connected to drought. It's more of a long-term trend, a drying trend. But it may also be worsened by drought. Famine is also something that's sometimes linked to drought or connected to drought in media reports, for example. And famine actually refers to a widespread scarcity of food, which can be caused by several factors, like a crop failure, which can be drought affected, but it can also be caused by other aspects. And here we should highlight the government and governance aspects, and how governance affects vulnerability towards water or food scarcity, for example. So drought may lead to famine if the system is very dependent on local food production and rain-fed agriculture, for example. But if there are mechanisms to avoid this, if there is maybe some reliance on external inputs, then the situation may be different, maybe more about affordability of food. Excuse me. And then finally, is drought a disaster? And this is something that's debated within the disaster risk field. That is, drought is not a disaster by itself, but it can become a disaster if the effects on local populations are very strong. And that is about how vulnerable people are towards a drought. So drought is not necessarily a disaster by itself, but together with compounding factors, it can become one. Okay. We have some biophysical effects of drought, and these are just some examples. Maybe you can think of more or others related to where you are working. But we have biophysical effects, for example, increased risk of dust storms, land degradation, land getting salinized, more salt in the soils, wildfires, insect problems. We can also have socioeconomic effects of drought, for example, loss of yield, loss of livestock, lack of sanitation, which can have severe impacts on public health, wells that dry out, and increased cost for irrigation. You may need to pump up more water to irrigate. It's costly. It may lead to unemployment, people losing their livelihoods, and also it may affect hydropower. There is some evidence showing that droughts may lead to increased migration, where people migrate to secure livelihoods elsewhere. But there's also research showing that drought may decrease the risk of migration. So people migrate less if the drought, for example, leads to a situation where they cannot afford to migrate. And also linked to that migration is how drought can maybe worsen the risk of conflict. There are examples in, for example, talking about how the Syrian civil war was preceded by a very severe drought, and some analysts then link this drought to the war, or link the war to the drought. And this is, of course, relevant because drought puts a strain on the available resources. It makes things harder for people, but it's important to understand what context the drought happened in and what context a war happens in, because it's rarely just one reason for a conflict to start. Okay, so drought and climate change are quite connected, and I'm gonna turn off. No, I cannot turn off my video, so you will have to guess what the chart looks like behind me. But hopefully you can also access the slides without this video. So what I want to say here is that the latest climate report from the United Nations, the IPCC report, Assessment Report 6, states that the total land area subject to increasing drought frequency and intensity will expand in the future. So this means that there will be more areas that see increasing drought frequency. Droughts will come more often. And in the maps to the right here, we see that brown areas show an increased likelihood of drought years, and green areas show a reduced likelihood. Now, with just 1.5 degrees of warming, we don't have a lot of dark brown areas, but we have quite a lot of bright brown, yellow areas, and also some blue-green areas, which shows a reduced likelihood. But as we increase the warming level, we see more and more increased likelihood of droughts. For example, in the Mediterranean area, in China, South America, North America, many areas with dark brown colors, which then indicate an increased likelihood of drought. We still have some areas where we can see maybe a reduced likelihood of drought, but the areas with increasing likelihood are definitely more. We also see the slides here to the right. We can take the South American monsoon as an example, but all these three charts show more or less the same, that the soil moisture anomalies that are predicted for the future are mostly negative. So soil moisture can be an indicator of agricultural drought, which means that we are likely to see more agricultural drought in the future in the Mediterranean, in South America, and in West and South Africa, probably in other parts of the world as well. So when it comes to measuring drought, there are many different ways, and here the definitions that we use of drought can be very useful. So for meteorological drought, there are many different drought indices that you can look into, usually based on precipitation, sometimes based on temperature as well. A very straightforward index that I have been using is the Standard Precipitation Index, the SPI, which was developed in 1993. And it allows for a cross-region comparison, which means that you can compare a generally very dry area to a more moist area and still see if there was a drought or not. So this is good. I mean, that's what it means when it says standard or standardized. And what it measures is basically the number of standard deviations that the observed value deviates from the long-term mean. So we first have to establish a mean period or a long-term mean period. what is the long-term mean, what is the normal situation, and then we look at the number of standard deviations. And in this chart up here, we can see the normal distribution. So if your data is normally distributed like this, you have most values occurring around the mean value. So around 68% of the values are within 1 standard deviation from the mean on both sides. And then you have these areas which are less common values that are further away from the mean. And these are the areas where you can see, for example, drought. So according to the SBI definition or classification, if you are within 1 standard deviation of the mean, the situation is near normal. It's not really wet or dry, quite normal. If it goes below -1 standard deviations, you have a moderately dry situation. If it goes below -1.5, severely dry. If it goes below -2, it's extremely dry. So this is quite uncommon that you have values down to -2 according to this classification, right? And then you have on the other side, you have wetter years also. So I would say that the SBI is quite useful, and it's also good because it guides somehow what the values mean, because in some cases it's hard to know what is a drought, where's the threshold for a drought. And here we can say that if it's outside or if it's below -1 standard deviation from the mean, then we have moderate drought. Okay, so that's important. But of course, if you only look at precipitation and you don't consider the temperature, which is quite important for water availability, as high temperatures lead to evapotranspiration, we miss some part of this. We can have normal rainfall, but maybe the temperatures are quite high. So then we can look into the standardized precipitation evapotranspiration index instead, SPEI. So in a nutshell, it looks at precipitation minus potential evapotranspiration. And it's also standardized, so it's comparable across different regions. And I have a link down there, but it's not visible because of my my face here. But we will provide it elsewhere, okay? So here I have put an example time series over the Indochina Peninsula, and it says SPEI 3 here, and this means that SPEI usually comes with an aggregation of several months of data, which makes sense because usually you don't have a drought over just 1 month affecting anything, but if you have it over 3 months or 6 months, like, it's relevant to look over a longer time period. So for example, if you are looking at SPEI 3 for the month of March, it also includes data for the month of January and February, right? So it includes the former months data. So this is the region that I'm looking at. This is also from the link that I mentioned in the past slide that we cannot see because my image cannot be moved, but it shows the time series from 1950 to 2020, and you can see that most values are within 1 standard deviation from normal, but some values are above 1 and some are below -1. So the below -1s refer to or indicate drought years. And there are a few ones here. I mean, probably here we have a quite extreme dry period just before 1990, late 1980s. Since then, it hasn't crossed the -2 boundary, but it's quite close here in This is maybe 2017 or something. So this kind of time series can be quite interesting. Now it's important to note that this is averaged over quite a large area, or aggregated over a large area, so it doesn't really show variations within. It's just taken the whole area to look at the time series, but it gives you an indication of which years or which periods have dry weather conditions. Yeah, when you are looking at meteorological drought, there are different data sets that can be useful. Usually it's quite common to use weather station data that is collected nationally often. But in some cases, these data are incomplete, unavailable, doesn't have a long record enough, and then there are some alternatives. For example, there are global climate data sets that you can download, often in some sort of raster format. They have generally been interpolated over a larger area, so you have to be a bit aware of whether there is data that the interpolation covers or if it's interpolated based on very few data points. But some examples that are quite commonly used are the Global Precipitation Climatology Center data, GPCC. There's also the Climate Research Unit Gridded Time Series data, CRU, TS. There's WorldClim, which has historical climate data, also linked to CRU or using downscaled CRU data. But if you are working on an area that doesn't have a good record of weather station data, because you can see how many points the interpolation in these climate data sets are based on, you may want to use an Earth observation-based measurement instead. For example, the Tropical Rainfall Measuring Mission, which has sadly ended, but provides data for quite a long time period, or the Climate Hazards Group Infrared Precipitation with Station data, which is a combination of Earth observation data and weather station data, which I think is really good. And these Earth observation-based measurements are using, they're measuring the size of clouds to estimate the amount of rainfall that will fall over an area. So it is an estimation, but it's quite frequently used and can be quite useful in areas where you have big data gaps. So we move on to hydrological drought, and I don't have as much to say about hydrological drought, other than a reminder that hydrological drought can be measured by looking at river flows, water levels in lakes and dams, groundwater levels, and usually it's quite hard to study hydrological drought if you are in an area that doesn't have national measurements on, for example, river flows or groundwater levels. But there are remote sensing or Earth observation alternatives. For example, NASA has a Gravity Recovery and Climate Experiment project, the GRACE project, which uses gravity. So it's a satellite-based product that uses gravity to measure the groundwater level or assess groundwater levels across the globe. It also dates back to the early 2000s, I think, and it's really can be really useful to look at groundwater levels. So this is one alternative for studying hydrological drought. Yeah, agricultural drought then, and this is where I think Earth observation is specifically useful, because we have the ability to measure the Earth's reflection of vegetation, for example, or vegetation's reflection of light. or electromagnetic radiation. And we know by looking at spectral signatures that green vegetation has a higher reflection in infrared than, for example, dry vegetation has. We also know that green vegetation has a very low reflection in the red wavelengths, whereas drier vegetation has a higher reflection in red, in the red band, which gives us a very good ability to study vegetation patterns, vegetation health, vegetation density. And if we look at this false color composite here, which I think is from Vietnam, it's captured by Sentinel in 2024, so it's quite recent. It's a false color composite. It shows red, infrared as red. So all these red areas are near infrared, high reflectance of near infrared, and we can see that these are agricultural fields having a very high reflectance, whereas maybe other areas have a lower infrared reflectance. And because we know these things, we can use vegetation indices to study agricultural drought. So you have probably talked about the normalized difference vegetation index or heard about it before, the NDVI, which uses a comparison between near infrared and red reflectance and then divided by the sum of near infrared and red. It's a very simple, straightforward, very commonly used index, and it provides a value between -1 and 1, and all negatives values are basically water, although water is generally around 0. Bare soils are between 0.1 to 0.2, so it has a low value, and then vegetation has values ranging from 0.3 to 1. So depending on the health of the vegetation, you get a higher or lower number. And this can then be used in a standardization or standardization of anomalies. So because drought, again, is relative to what's normal, we have to compare the situation for the year of interest to the long-term normal situation. And then if we want to be able to compare different types of areas, if we're looking at a country with big differences between north and south or east and west, we want it to be standardized to see maybe what areas are worst affected. Okay, so here we can work with z-scores. And z-scores are a very simple way to measure anomalies. And they are similar, I mean, they give a similar value to the SPI or similar, a similar method to the SPI. So you compare the score of the period you're interested in with the long-term mean, and then you divide it by the standard deviation. And this gives you the number of standard deviations that a value deviates from the long-term mean. So I've re-added this this table here showing the z-scores values and what they would refer to if they are near normal, between 1 and -1 standard deviation, or going to drier, below -1 standard deviation. So this is a very good way to study agricultural drought, to identify vegetation anomalies. Okay. One thing to think about though is that not all vegetation anomalies are linked to drought. You can have anomalies due to clearing of forests, for example. In some areas you might have a change in land cover, change in land use, which may reflect as an anomaly. So you have to understand the context, of course, and maybe also look at other measures of drought to see if the NDVI anomaly is actually linked to a dry period. Yeah. Then we have the definition or the class socioeconomic drought, which is slightly more difficult to measure. I would say it's a very important class of drought that needs more attention, but it's not as straightforward how we can study it. But there are some suggestions here that I will just mention. For example, looking at food prices, if the context of your study is an area where you have a high local agricultural production of food, then a drought may influence food prices, which says something about how people are affected by the drought. You can also look at household incomes, for example, if you're looking at an area where you have a high dependence on agriculture, household incomes, or the ability to eat. Usually it's hard to study socioeconomic drought with remote sensing or Earth observation data. Here it's more relevant to look at survey data, maybe already existing survey data, or conducting a survey about the drought, or doing interviews with people. So I just wanted to add that, and that can sometimes, a socioeconomic drought assessment using interviews or surveys can be a good complement to an Earth observation-based study of drought, for example. Yeah, so I've reached the end of this lecture, so I'll just take a short summary so you know what I really want you to take with you from this lecture. And the first one is that drought is temporary and relative. So it's not a permanent situation. It's a deviation from the normal situation, okay? And it's relative to what is already normal. Which is why it's good to use a measure that is standardized, because then you can compare drought across different places. There are 4 classes or definitions of drought. Meteorological, the most common one, looks at precipitation and temperature. Hydrological drought looks at water levels in different water bodies, groundwater reservoirs, rivers, for example. Agricultural drought focuses on vegetation and maybe more on agricultural vegetation. Is there enough water to support crop growth? And then socioeconomic focuses on people. How are people affected by the drought? We can measure it in different ways. Weather station data is quite common, but there are situations when you don't have access to good weather station data, and then satellite data can be a useful replacement for that. That's all I had to talk about for now. Thank you very much for listening and have a nice day.